Okay, today we want to look at section 6.6, still on mathematical induction, but this time we're going to talk about strong induction, which sounds different, but is technically the same as weak induction, or what we've been doing before, and how it's related to what's called the principle of well ordering, or the well ordering principle. So this first example lets us see how we could use both methods, strong induction and well ordering, to solve the same problem. So let's read the question first. So prove that any amount of postage worth 24 cents or more can be made from 7-cent or 5-cent stamps. So really we're saying that, the number 20 or any number 24 or more can be made by combinations of 7s and 5s. And so in strong induction, instead of just using the one before it, like if we use our domino example again, we have all these dominoes. And with weak induction, we assume the one before it can knock over the one after it, or we prove this statement by just using the one before it. Well, we call that weak because it's only using part of the knowledge you have. In fact, you could, if this one's knocked over, then every one of them before it's knocked over as well. So you can use all of these statements to come together to prove the next one. So that's really what strong induction is. We assume all the statements less than k plus 1, or less than or equal to k, is true, and use that to prove the k plus 1 statement. We need strong induction when we can't just go back by 1. Like in this case, we kind of have to start by looking at the first few possibilities. So like 24 cents. That could be 2 5-cent stamps, 2 5-cent stamps, and 2 7-cent stamps. So 10 and 14, that's 24. And we're going to go all the way up to 28. So we have to sort of check the first 5 cases here. So 25, of course, is 5 5-cent stamps. 26 cents could be 1 5-cent and 3 7-cents. 27 could be 4 5-cent stamps along with 1 7-cent stamp. It's 20 plus 7. And then finally 28 we can just do with 7-cent stamps. We have 4 of them. So we're going to set that off to our side as essentially our base case. So instead of one thing that we have to prove at the beginning, we had to prove 5. And the reason we have to start with 5 is because how the induction is going to work, we're going to take some number k, or assume that all values k or below can be made with combinations of 7 and 5-cent stamps. And so we need to sort of pull out either a 7 or a 5. Of course, 5 is the easier one to work with. And so we'll end up with 5 below where we started. So we have to have sort of a buffer of 5 here in order to make the induction work. So since we're good from 24 to 28, we can suppose k is bigger than 28. Or actually, we can say greater than or equal to 28. Yeah. And so 28 we know works, but k plus 1 could be as small as 29 here. So that's the one we want to show works. So we assume the statement is true. Not just for k, but for n less than or equal to k. So everything below. So if this is k, we're assuming all of these before it are also true, up to our base case, which in this case is 24. So now we need to show that it's true for k plus 1. So I'll circle that show true for k plus 1, we'll just say cents. Circle that because that's what we want to show. Well, k plus 1 is at least 28, or sorry, at least 29. So that means k plus 1 minus 5 would be k minus 4 is at least 24. So k minus 4 is greater than or equal to 24. So it's not too small. It's not outside of our range. And of course, it's smaller than k. So it's here somewhere, right? It's k minus 4 would be back here, so we can use it. And so that means the statement is true for k minus 4 cents. True for k minus 4 cents. And well, that's great, because if it's true for k minus 4 cents, all we have to do is add the 5-cent stamp to that to get a combination that gives us k plus 1. So inserting a 5-cent stamp into what we have, we're saying that if the statement is true for k minus 4, then k minus 4 is written as, or can be made as a combination of 7 and 5-cent stamps into the k minus 4, k minus 4, making the statement true for k plus 1. And that's it. So with my remaining space here, I'll do the well-ordering version. And hopefully you've already read in Zybooks the definition of well-ordering, but we'll state it here. Just that every set of positive integers has a smallest element. And so we end up proving by contradiction. We say, let S be the set of integers where that can't be made from 7 and 5-cent stamps. So where the statement is false. Of course, if this set is empty, which is kind of what we want here, then we have no well ordering. There's no smallest element if you don't have anything in your set. But we're going by contradiction. So we're assuming that there is values that can't be made from 7 and 5-cent stamps greater than 24, or greater than or equal to 24. So that means S has a smallest element. So by well ordering, S has a smallest element. We'll call it N. But we're going to use this again. Might as well not waste all that work. And say, well, N is at least 29. So we'll say and N is at least 29. But that means N minus 5 is at least 24. So since N was the smallest element where that can't be written as 7 and 5-cent stamps, N minus 5 is smaller, and it's in that range so that it works. So, or it's not too small, essentially. So that means N minus 5 can be written as 7 and 5-cent stamps. It can be written as 7 and 5-cent. But similar to what we saw here, this was k plus 1 and k minus 4. Here we have n and n minus 5, but same difference. We add a 5-cent stamp to what we got from here, and now we have something for n. But that contradicts that n was working. So that means, once again, inserting a 5-cent stamp. So again, it's really, well ordering is pretty much the same as induction. It just feels a bit different. So n can be written as 7 and 5 cent. But that's our contradiction, because n was assumed to be a value where the statement was false. Okay. Another place we use strong induction is in recurrence relations where you have to go back more than one. So before we saw examples of recurrence relations that really only went back to the one before in the sequence. But if you go back more than that, then you technically have to use strong induction. And of course we'll use the famous one, the Fibonacci sequence. Starts as 0 and 1, and then every value is just the sum of the two before it. So 0 plus 1, 1. 1 plus 1 is 2. 2 plus 1, 3. 5, 8, 13, and so on. Well, it turns out the formula for the Fibonacci sequence is a bit complicated. Having these two values, 1 plus root 5 over 2 raised to the n, and 1 minus root 5 over 2 raised to the n. So for convenience, we're going to call this one phi1. Calling it phi because 1 plus root 5 over 2 is the golden ratio, which is usually denoted by the Greek letter phi. And then we'll call the other one phi2. Now, these, you can kind of imagine coming out of a quadratic equation with the plus or minus in front of a square root. And so these are actually the roots to x squared equals x plus 1. So has solutions phi1 and phi2. That's going to be important, at least to make this, doable in a small amount of space. You could certainly do this problem using these values, but you're going to hate yourself at the end. Okay, so with this type of induction, we have to check the first two cases, similar to in this problem where we had to check the first 5. So the first two cases, f0 should be 0, and it should be 1 over root 5 phi1 to the 0 minus phi2 to the 0. But that's 1 minus 1, so that's going to be 0. And then f1 is 1 over root 5, and then phi1 minus phi2, because just both to the first power, which is 2. Well, if you look at these, if you subtract these, you end up with the 1/2s canceling out, and you end up adding the two root 5s together. So subtracting these gives you root 5. And of course that cancels out with this root 5, so giving us 1. Now for the inductive step, we assume it's true for n less than or equal to k. So before we said n equals to k, but now we're going to use everything before k and prove that it's true at k plus 1. So f of k plus 1, by definition, so similar to how we prove the other recurrences, is fk, the one before it, plus the one before that, fk minus 1. But by induction, fk would be this with k's in the exponents, and fk minus 1, since that's also smaller than k, would be this one with k minus 1s in the exponents. So you can see why I want to write it as phis. So this times phi1 to the k minus phi2 to the k, and then plus 1 over root 5 v1 to k minus 1 minus v2 k minus 1. Now the 1 over root 5 is not really going to come into play. Its only purpose was really to make this a 1 in one of the base cases. So it gets factored out, and we're just going to see how all the phis combine. So we have these two are added together, so phi1 to the k plus phi2 to the k minus 1. And then these two are both subtracted, so I can factor that out. And phi2, or sorry, yeah, phi2 to the k plus phi2 to the k minus 1. I'll put these in parentheses too to make it look nicer. In both of these you have, oops, this should have been 1 as well. We put the 1s together and then the 2s together. So you have something you can factor out. You can factor out k minus 1 of the phi1s. And you're left with phi1 plus 1. And same thing here. I can factor out k minus 1 of the phi2s. And now that's where we're finally going to use this. We have that for both of these. If I add 1, I get that value squared. So this is going to be phi2 squared, or sorry, phi1 squared, and this one's going to be phi2 squared. And that's going to bump it up exactly as much as we need. I ran out of room here, but you can see adding these exponents together will give me k plus 1. Adding these two together, k plus 1 here as well. So it gives me the next case. We'll do a couple more examples with recurrences. Similar idea with the Fibonacci one. We have a recurrence that relies on the 2 before it, but 5 times the 1 just before it, minus 6 times the 2 before it, and then 20 times 7 raised to the n. So a lot going on here, but turns out it's not going to be too bad. A little bit messy, but not too bad. We're trying to prove that it actually comes out really nice. It becomes 2 to the n, 3 to the n, and 7 to the n plus 2. Okay, so we can check the first few cases. So we'll put that up here. H0 would be 2 to the 0 plus 3 to the 0 plus 7 to the 2. So that's 1, 1, and 49, so that is 51. H1 would be 2 to the 1 plus 3 to the 1 plus 7 cubed. And 7 cubed is 343, so plus 5, so that is 348. Okay, now we just want to show that this also works with this recurrence. So we assume that it's true for n less than or equal to k, and we want to prove it for h k plus 1. So we look at hk plus 1. By definition, it's 5 times hk, the one just before it, minus 6 times hk minus 1, the one before that. And then plus 20 times 7 to the, our k here is k plus 1, so it'll be k plus 1. But each of these, hk will be exactly this. hk minus 1 will be this with k minus 1s in place. So this is where we get a bunch of algebra. So we have 5, 2 to the k, 3 to the k, plus 7 to the k plus 2, and then minus 6. Oops, missed the h there. And now 2 to the k minus 1. 3 to the k minus 1, and then 7 to the k minus 1 plus 2, so k plus 1. And we still have this guy at the end. So again, we want to combine like terms here, which is really to say combine like powers. So the powers of 2 we're going to put together, the powers of 3, and the powers of 7. So for powers of 2, we have 5 times 2 to the k. And we're going to subtract 6 times 2 to the k minus 1. We have 5 times 3 to the k minus 6 times 3 to the k minus 1. And then for all the 7s, we have 5 times 7 to the k plus 2 minus 6 times 7 to the k plus 1, and still our 20 times 7 to the k plus 1. Okay, now we have to do sort of similar tricks that we've been doing with these powers. Like we could pull a 2 out of here to get the common k minus 1. That would give me 10 minus 6 k minus 1, so that's 4 times 2 to the k minus 1. Similar thing here, we'll pull a 3 out of here, making that a 15. Minus 6 would be 9. You can see how that's going to bump everything up, because 4 is 2 squared, so it's going to bump this up to k plus 1, which is exactly what we want. Same thing here, 9 is 3 squared, bumping that up to k plus 1. So that handles these two and these two. Now we just have the 7s, which we have to do in a couple steps here. So leaving this one alone. We first want to put these two together because we're going to get 14, 7 to the k plus 1, and then we can pull a 7 out of that 14, bumping it up to k plus 2, and that'll leave with 2. So I have 2, 7 to the k plus 2 from these two going together. And we're pretty much there. So this is 2k plus 1, 3k plus 1, and here you have 5 and 2 of the 7 to the k plus 1, so you have 7 times 7 to the k plus 2. So that gives you 7 to the k plus 3, which is, again, exactly what we want. Okay, let's take a look at our last one. So here we have a sequence where the first 3 terms are 1, and then every term is the sum of the 3 before. So kind of similar Fibonacci, where instead of adding the 2 before it, it's the 3 before it. So you get 3, and then 3, 1, 1 is 5, 5, 3, 1 is 9, 3, 5, that's 17, and so on. So we don't actually want the formula for this one. The formula would be crazy hard. It's amazing how hard these get once you start adding further and further back. Not all of them will be, but in general they are. It's basically, if you go 2 back and you end up with a quadratic most of the time, 3 back will give you a cubic. And so the general cubic, you may have seen the formula, the cubic formula, is really, really horrible looking. So we're definitely not going to do that, but we will prove that each value is less than 2 to the n. So we're saying this is less than 2, this one's less than 4. So at the beginning, it seems kind of obvious that they're going to be less than 2 to the n, but this starts to grow pretty fast, but it doesn't get any bigger than 2 to the n. So the base case is just to show that those first 3, a1 is 1, and that's less than 2 to the 1. a2 is also 1, and that's less than 2 squared. And a3 is also 1, less than 2 cubed. So those pretty clearly check out. Now, we assume that this inequality is true for n less than or equal to k. And we look at k plus 1. We look at a k plus 1. We want to show that this is less than 2 to the k plus 1. So that'll be our goal here. Well, by definition, it's equal to the 3 before it, or the sum of the 3 before it. So ak plus ak minus 1 plus ak minus 2. But we can use our induction hypothesis on all three of these. We can say this one is less than 2 to the k. We can say this one is less than 2 to the k minus 1. And this one is less than 2 to the k minus 2. So the sum of these three are less than the sum of these three. Now we want to show that this is smaller than 2 to the k plus 1. So we're going to start putting things together. The first observation we're going to make it smaller than something, copying these two, but then bumping this up by a power. So 2 to the k minus 1. So that's essentially multiplying this one by 2, which is going to make the sum bigger, right? You're multiplying a positive number by 2 and then adding it to the other two. So this is now bigger. But this is nice because we can add all this together. So putting these two together would give you 2 times 2 to the k minus 1. So that would give you 2 to the k. And then 2 to the k's give you 2 to the k plus 1. Oops. Move that up. So basically, if you add any powers of 2 together, like 8 and 8 are both powers of 2, they give you the next power of 2, right? So these 2 powers of 2 give you the next one, these 2 powers of 2 give you the next one. So we have what we want. We have ak plus 1 is smaller than 2 to the k plus 1. Okay, so this catches us up on what we were supposed to have done by Thursday, but I was falling a little bit behind. I'm trying to catch up. I'm finishing this one on Saturday, although I'll probably post it on Tuesday when I get back to campus, because my download speed is, or my upload speed is extremely slow at home, so it's not really worth it. And then I'm going to continue working this weekend and Monday, getting the next 3 sections done, so that we'll have all that up by Tuesday. Okay.